Zoe Huaf, who is visiting with us as part of an interview to join faculty. She got her bachelor's degree in chemistry from Ohio Wesleyan University, which they refer to there as OWU. And so,
very good.
In the event that she refers to Mercer University as Moo, it is not her fault. That's an Ohio thing, so you have to forgive her. All right. Now she is at Purdue University, where she is a PhD candidate in an interdisciplinary program. She is in medicinal chemistry and molecular pharmacology, and her expertise area is applying molecular dynamics, simulations, methods to biomolecules. Her lecture today is going to be a brief lecture on molecular shape, which hopefully is a review for everybody here, but if you are taking notes, I'm not going to hold it against you. And then we are also going to be reconvening in this same room at 1:30, at which point we're going to talk a little bit about or actually Zoe is going to talk a little bit about research project ideas related to her expertise. So 1:30 back here. For now though, I am going to turn it over to you.
And I'm almost done. Give me 1 second. Okay, so thank you everyone for coming here. Can you give me? So my name is Zoe. Go ahead and call me Zoe during class because I am not a doctor yet. Hopefully by the summer. So you will have in front of you a reference table that I will refer to during class, and also stacks of color-coded letters A, B, and C that we will be using during class today. So let's get started. Okay. So if I ask you a question, how many of you here think that molecular geometry is important? Okay, you cannot raise your hand just because your friend raises their hand. That is not fair. So now, honestly, how many people here think it's important? Okay, most but not all. But if I ask you how many people here think that finding a drug that can treat cancer is important, now raise your hand if you think it's yes. Of course, it's important. Cancer is one of the big diseases that everybody want to cure. So actually, as it turns out, there's a molecule, let's call it molecule A for now, that causes cancer, and it has a certain pocket that has that shape. And then a guy, a medicinal chemist, came up to me and say that there are these 3 drugs that can treat cancer that have this shape. And now if I ask you, how many of you here think that particular one is going to be the most favorable one? Raise your hand if you think it's yes. Yes, you are correct. Good job. You passed the first question. So, as it turns out, drug efficacy depends on shape complementation. And the fact that this guy can fit right into this pocket allows it to be the most favorable drug. And so the shape of a molecule is essentially its molecular geometry, and we just established that it's important. Okay? So for today's class, the goal is you will learn to determine the molecular geometry and the molecular polarity from a chemical formula. You will learn how to draw the molecular geometry. And also you need to know the definition of a few terms, which we're going to do right now. So the way it's going to work is that I am going to go through a few examples. I'm going to start easy and show you how to proceed with determining the molecular structure. And then I'm going to turn the floor over to you. I'm going to be asking you a lot of questions. You're going to answer the questions and eventually find the answer on your own. And as we go through the example, I'm going to add on a few important concepts. Before that, let's get through the definition. So the first definition, an electron domain. An electron domain is defined to be a lone pair or a bond. Okay, so if you have a triple bond, it is still one single electron domain. But if you have two lone pairs, you have two electron domains. So when I ask you for the electron domain geometry, I ask you for the 3D arrangement that involves bond and lone pairs. Okay? Important word and. And if I ask you for the molecular geometry, I want you to find the 3D arrangement that involves only the bonds. Okay? So don't get that confused because it gets confusing very quickly. Okay. So, first example, easy ones. Carbon dioxide. So I show up here basically a step-by-step way to determine the molecular geometry from a formula. So, Jordan, you told me your name first, so you can go first. So carbon dioxide, tell me, what do you think is the central atom of this molecule?
It's probably carbon.
It's probably carbon. It is carbon. So, carbon is in the center, and then you have two oxygen on the side. So now, from your chemical knowledge of classes before this one, what kind of bond can oxygen form with carbon? Everyone? Double bond. So for double bond, you draw two electron pairs, and the other side, same thing. Okay, so we want to find the molecular geometry of the central atom only, so we really care just about the Lewis dot structure around the central atom. Okay, so now is carbon happy? It is happy, so we can move on to the next step. Alright, so count the number of electron domains. How many people think? Are you raising your hand?
No.
Oh, no? I was hoping that you would. Okay, so it's the first example I'm going to tell you. There are two bonds surrounding carbon, no lone pairs. So essentially there are two electron domains. Okay? And now the next step, you want to find the electron domain geometry. So to find it, imagine you're going to draw balloons around the carbon atom. So if I draw it that way, because that's the way that the Lewis dot structure is shown, this shape, when you have two balloons on almost a straight line, the shape is called linear. Okay? And now, to go from electron domain geometry to molecular geometry, you would erase any balloon that corresponds to a lone pair. Is there any balloon here that I should erase? No, because this one is a double bond and that is also a double bond. So the shape has not changed. So the shape or the molecular geometry for this molecule is still linear. Okay? Good. So that was easy. So the way you will show it on your test or quiz or homework is you're going to have a degree, to the value of the degree to show the angle. Because it is a straight line, the angle between these two bonds is 180 degrees. Okay? If you don't show the numbers, I will not take it as the correct answer because you can draw whatever you want. And if you don't show the number, it's not completely clear that you understand it from my point of view. Okay? So that was easy. I did that. The next one will be your turn. Okay, so next one, ozone. First question. Kadrian, tell me, what is the central atom on ozone?
Guess the oxygen.
Yeah, exactly. There are 3 oxygen, of course, one of them is going to be the center. So now, quick question, have you learned resonance yet? Yeah? Oh, okay. Alright, in that event, so children, around this oxygen, what kind of bonds can this central oxygen form with the oxygen on the left? It can be a double or a single, so for the sake of simplicity, let's say it forms a double bond. And then on the right, for the sake of simplicity, let's say it forms a single bond. And so you have a single lone pair up here. Okay, so now how many electron domains are there on this molecule, on this central atom? Someone else that I don't know the name of. Please volunteer.
3.
3, very good. So you have 3 electron domains. Can you tell me what are the 3 electron domains?
You have the lone pair,
Mm-hmm.
and you have the single bond and the double bond.
Very good. So now you need to draw the balloons. So how would you draw the balloon? And what's your name?
Pavel?
Pavel. How would you draw the balloons onto this oxygen atom?
You would draw 3 balloons around the oxygen.
So this way,
More space. So
more space. Why did you tell me to draw more space? Why?
sure.
So
that there's equal spacing between each balloon.
and why is that?
You minimize the electron repulsion.
Very good, very good. So you already answered the question that I am about to have. So the correct version is supposed to be this one. And the reason is, if you imagine, you're going to have negative charges on the balloons because they contain electrons. And 2 negative charge, do they want to be near one another? No. They don't want to be near one another, especially when you have all the space down here that balloons can fill up. And that's why they push one another as far away as possible. And that essentially is the valence shell electron pair repulsion. It says electrons pairs in the valence shell repel, and they want to be as far away from one another as possible. Okay, so that's good. Now, I want you to refer to your reference table and tell me for 3 electron domains with this particular shape, what is the electron domain geometry? I'm going to point to someone else.
It should be trigonoplanar.
Trigonal planar, very good. Because it looks like a triangle. Okay, very good. So now to go from electron domain geometry to molecular geometry, you want to erase the balloon that corresponds to the lone pair. So let's say I fill in, that is the lone pair, that is the double bond, and that is the single bond. What balloon should I erase? The top one. So if I erase that, the shape, is it linear? No. And this particular shape is called bend. Okay? You cannot go directly to molecular geometry. You need to have the step of electron domain geometry. Okay? Alright. So I said that. And to show it, you need to show the angle here. And this angle is approximately 120 degrees. It is not quite exactly 120 degrees. And there's a reason. Any idea? You're supposed to pretend that you don't know. So it's okay if you look at me blankly. Okay. So the reason is, right now, this molecule still have a lone pair up here. Okay? And lone pair repel more strongly than bonding pairs. So that means between this lone pair and this bonding pair, the angle is actually more than 120 degrees. And the same on the other side. So now by mathematical rules, this one will be less than 120 degrees. On the exam though, you can just show approximately 120 degrees. Unless I ask specifically, is it going to be smaller or larger, and why? You will see the question why very often. Okay? All right. So I told you earlier a term that we haven't defined yet, molecular polarity. So what is molecular polarity? Molecular polarity is a direct consequence of molecular geometry. The reason why we want to know what is the molecular polarity of a molecule is because we need to know if it is polar or non-polar. Whether it's polar or non-polar will affect directly the physical, chemical, and biological properties of a molecule. So while we are at it, let's find the molecular polarity of this molecule. Okay? So to find the molecular polarity of a molecule, we need to understand dipole. Do you remember from your class? What is a dipole? Have you learned it before? Yes? Okay. So for a dipole arises from what? Polar bond. From charge difference. From polar bonds. So the oxygen and the oxygen bond here, is it polar? How many people think no? It's okay to say no. It's okay to don't know. It's okay to say no also. Okay, so let's do this one first. It's easier. This oxygen right now, for the sake of simplicity, has a positive charge. And this oxygen right now has a negative charge. Do you think that that bond is a polar bond? Yes. And the polar and the dipole will point towards the negative ends. Okay? So now for this guy, one is neutral, one is positive. Which one is more negative? The neutral one. Very good. So you're going to point the dipole towards the neutral oxygen. So to determine polarity, thankfully this molecule is planar, so you can work on it on the board. So we're going to draw the xy coordinates. Okay? And the way we're going to do it is we're going to translate this dipole here all the way down here so that the tail of the arrow touch the origin. So essentially, I'm going to draw an arrow like that. And then the same for the other dipole. Okay? So now, this molecule will have dipole along two directions. And to determine the polarity, you need to know the net dipole along each direction. So we're going to project this dipole onto the x-axis and that dipole onto the y-axis. Okay? Dipoles are additive. So if you have an x component towards the positive side and an x component towards the negative side, do they cancel out? Yes. And the net dipole along the x-axis will be 0. Some of you show your answer through body language. It's okay to hold your answer. Okay, so now along the y-axis, we're going to do the same thing. So we're going to project this dipole onto the y-axis. And then for that dipole, because dipole are additive, we're going to have to add another arrow. So this is the total net dipole along the y-axis. Is it 0? No. So the net dipole along the y-axis is not 0, and that is why this molecule is polar. Okay? Okay, very good. So I said that. So we went through two examples. What have we learned so far? We learned the valence shell, electron pair repulsion. It essentially tells you that the electron pairs in the same valence shell repel, and they want to be as far away from one another as possible. And we also learned from this example, most particularly, that lone pairs will repel more strongly than bonding pairs. And it's very important. Okay? And also, from this example, you can see that the electron domain geometry is not always the same as the molecular geometry. But then in this example, they are the same. So they are only the same when you have no electron lone pair. Okay? Only when there's no lone pair. But that's good. If you know there's no lone pair, you only should have to find one geometry. Okay? Alright. Next example, a little harder. Carbon tetrachloride. Okay. So, carbon tetrachloride, I'm going to give you the easy stuff. Carbon is a central atom. Who want to volunteer to draw the structure? Raise your hand before I start pointing at you. Okay, she's going to do it. If you are in my class, you can expect this very often. Thank you. Very good. Thank you. See, this was easy. It's not that hard, guys. Okay. So carbon forms single bond with chlorine. So I'm going to replace it with electrons for now. So how many electron domains are there around the carbon atom? 4. So 4 electron domains. So now go ahead and refer to your reference table. What kind of electron domain geometry is that? Tetrahedral. Good. So in class, and when you do homework, you have a reference table. And the idea is that you will do enough homework that by the time you take your quiz, you would have all that memorized. Okay? So I will assign you a lot of homework so that you get that down. Okay, so tetrahedral. How can we draw a tetrahedral molecule? So that's a balloon. So you want to first start with drawing a semi-equilateral triangle, and then just draw another one like that. Okay? And that's good enough for me. And then of course you have to indicate the angle, which is 109.5 degrees. That's the standard shape. Okay? So now, without referencing table or without erasing any balloons, what is the molecular geometry for this molecule? Because, very good. Tetrahedral, because there is no lone pair on this molecule. Good. So you might have seen this before. This is also another valid way to draw the molecule. So you can see that there is the solid wedge. That means the molecule is pointing at you. And the dash wedge right here, that means it's pointing away from you towards the paper. And the 2 lines means the molecules are sitting on the plane of the paper. Okay? Now, harder question. How do you determine the polarity of a non-planar molecule? Of course, you can always draw that, but how do you do it in 3D? Right? So the trick, I'll tell you a trick. So this molecule right here has no lone pair, and all the atoms surrounding it are the same, right? You have 4 chlorine surrounding carbon with no lone pair. Whenever you have that case, the molecule will be nonpolar. Okay? So only when you have the central atom has no lone pair and everything around it is bonded to the identical atoms, then you have a nonpolar molecule without having to go through the dipoles and stuff. As soon as I change this one atom to hydrogen, this molecule is no longer nonpolar. Okay? Question up until this point? Clear? On to you. The way this is going to work is I'm going to show you a few multiple choice questions. You're going to have right in front of you A, B, and C. You're going to hold up. So I'm going to show you a question. I'm going to give you, say, 30 seconds to think about your answer. I'm going to ask you, can you show me your answer? And you're going to hold up your answer. Okay? Ready, everyone? Okay. First one, our favorite molecule, water. Up until this point, a little bit. Up until this point, I am still very much fascinated by water. Nobody completely can simulate or model it. Okay. First question, what is the electron domain geometry of water? Don't look at your friends. Okay, very good. All right, so it has 4 electron domains. We just went through that example. For 4 electron domains, the electron domain geometry is supposed to be tetrahedral. Now you know what the next question will be. It's quick.
Oh, is it?
If I teach you in class, I have to think of questions that you cannot predict them. What is the correct molecular geometry? Good. Oh, you are very good. Okay. Good. So it is band. We did this for ozone. Whenever you have this kind of shape, the name for it is band. And lastly, is this molecule polar or non-polar? Do not look at your friends. You're not supposed to look at your friend. It's okay to be wrong. This is when you learn, by the way. It's okay to make mistakes now. So this molecule is similar to ozone. You have a band shape, and each bond is polar. So overall, the molecule will be polar. Okay? That was quick and easy. There's another one coming up. Okay. All right. Next one. Sulfur hexafluoride. So this one has 6 bonds. Sulfur is a central atom and has 6 bonds around it. I told you that there is no lone pair on the sulfur. And then I asked you, what is the molecular geometry of this molecule? And Jordan. Oh, sorry. I thought I was about to. All right, Kadrian, you show B. Why did you decide on B?
Because 6 bonds around it, that's the shape.
So it has 6 bonds around it. And it has no lone pair. That means how many electron domains are there? 6 electron domains. So the shape, the electron domain geometry will be octahedral. And then I told you earlier, when you have no lone pair, the electron domain geometry and the molecular geometry is the same. So it should be octahedral. Okay? And last one. Is this a polar or non-polar molecule? And Pavel, why did you say it's non-polar?
It has the same substituents all around, so the dipoles will cancel.
Very good. It has no lone pair and everyone around it is identical. Good. Everyone got all the concepts down? Okay, so now on to to-do list when you get home. Of course, I couldn't cover everything in class. So when you go home, you're going to have to read up on deviation from standard geometries. Okay? We cover most standard shapes, but there are deviations, of course, as with everything in life. And you need to learn molecular geometry of molecules with multiple central atoms. Somehow, molecules with one central atom is not that interesting yet. We want to go bigger. And we want to know how it is shaped overall in 3D. And so I actually have the handout, but I didn't have time to give it out to you guys. I'm sorry. But the handout is supposed to help you with the reading, so consider it as guided reading. And it will be due the next class, in the beginning of class. So if you show up to class late, I am not going to take your homework. Okay? Don't forget that. All right. And that is the end of my lecture. Thank you very much. Any questions? As if you are students. Now, as if you are attendees. Okay, thank you very much.